At the start of 2025, the Greek island of Santorini was rattled by 28,000 earthquakes in a matter of weeks. A massive surge of magma moving through the crust triggered this specific seismic crisis. Researchers tracked 300 million cubic meters of magma pushing upward. It migrated northeast from Santorini, stalling near Colombo. The sheer volume fractured rock layers, causing the seafloor to bulge. This confirms local trigger mechanisms for marine hazards are active. This geologic volatility aligns with a statistical threat level recently published by UNESCO. Their models predict a 100% probability that a tsunami exceeding 1 meter will strike the Mediterranean Sea within the next 30 years. The Mediterranean is a highly pressurized geologic system loaded with 13 active volcanoes, capable of triggering sudden, catastrophic marine events. Regions like the French Riviera concentrate massive populations and economic infrastructure directly on the water's edge. Coastal infrastructure in these zones is engineered to withstand the impact of violent, wind-driven storm waves. Seismically generated tsunamis operate on fluid dynamics that differ significantly from those of a surface-level storm. Structural engineering often relies on a misunderstanding of wave physics that creates more risk than the actual height of the water. To see why modern seawalls are prone to failure, we must deconstruct the mathematical difference between how wind and water apply force to concrete.
Later.
Deep water wind waves grow continuously under the action of sustained winds. Their maximum size is limited by fetch, the total distance the wind blows uninterrupted over open water. In the Mediterranean, the dominant Maestrale wind has a limited fetch, which restricts local storm waves to roughly 5 to 7 meters in height. When a wind-driven wave breaks against a vertical breakwater, it traps a pocket of air. That air compresses between the water and the wall until it bursts. Coastal engineers use the Goda method to calculate this force. The resulting pressure distribution shows a sharp, localized spike exactly where that air cushion detonates. That impact is an explosion that lasts only milliseconds, and the pressure decays rapidly below distill waterline. Standard seawalls are designed to absorb and deflect these brief, surface-level aerated explosions.
1 hour later.
Tsunamis are shallow water waves. Their extraordinary wavelength puts the entire water column in motion from the seafloor to the surface. They impact structures as a sustained, high-velocity tide, lacking the compressible air cushion of a breaking storm wave. Calculating this horizontal force requires the Morrison equation. This model calculates 3 distinct vectors. The first is hydrostatic force, the baseline pressure exerted by the depth of the standing water. The second is drag force, generated by the sustained velocity of the fluid moving past and against the structure. The third is inertia force, caused by the massive acceleration of the entire ocean mass hitting the wall at once. Wave tank testing confirms that the combined force of a tsunami surge is 9 to 12 times greater than the baseline hydrostatic force alone. A tsunami is a sustained, crushing hydrodynamic load that wind wave test, a 4.3-meter wave impacting a standard vertical seawall. Using the Goda method, a 4.3-meter wind-driven wave exerts an average pressure of 28 kilonewtons per square meter. A 4.3-meter tsunami wave hitting that exact same wall exerts an average pressure of 238 kilonewtons per square meter. The tsunami creates a structural load more than 8 times higher than a storm wave of the exact same height. For context, industrial gas explosions are typically designed to exert around 35 kilonewtons per square meter. A standard seawall engineered to deflect a 5-meter storm wave will be instantly pulverized by a 5-meter tsunami. Applying this math illustrates the immediate nature of the crisis. The Mediterranean's enclosed geography removes the multi-hour warning window common in the Pacific. Consider a submarine landslide originating near Corsica or the North African coast. These waves rapidly propagate across the basin, heading directly toward the French Riviera. A wave triggered here leaves a warning window of only 15 to 90 minutes. Deep ocean buoy warning systems are ineffective under these highly compressed spatial constraints. In localized underwater landslides, the tsunami bore can strike the shore before an official alert is even processed. The combination of an 8-by structural pressure multiplier and virtually zero warning time makes the Mediterranean coastline uniquely vulnerable to infrastructure failure. The Mediterranean has suffered these catastrophic geologic impacts before, validating the threat models with historical precedent. Relying on static wind wave load limits is insufficient for protecting populations in closed basins. Future coastal resilience requires adopting dynamic tsunami multipliers into all baseline seawall designs. Engineers must calculate for wall permeability and sustained fluid drag to prevent structural collapse. Because concrete has physical limits, ultimate survival relies on hyper-fast evacuation logistics. Acknowledging the true physics of a tsunami bore is the only way to prepare presumed safe basins for the strike the data suggests is inevitable.